In this video, we're going to talk about what qubits are. We're going to introduce some of the notation that we use to describe and work with quantum bits, and I'm going to explain how all this stuff relates to probability amplitudes, which we went over in the last video. So I did mention in the last video that a qubit is a two-level quantum system. And what that means is essentially at any given moment in time, your qubit can be in one of two configurations. So physically, this is usually realized by some spinning particle that can either be spinning relative to this axis oriented up, or the axis could be oriented down. So this would be spin up and this would be spin down. And since these are quantum events, measuring one of these two configurations has an associated probability amplitude. And so we can call that alpha up and alpha down. And a good way to talk about qubits, since they require two complex numbers, is to use complex vectors. So for a qubit, for just a two-level system, we have a two vector. So it's specified by two complex numbers, alpha up and alpha down. And remember, at any given moment in time, the probability of measurement obeys Born's rule, which says that the probability of measuring, let's say, spin up will be equal to the probability amplitude of spin up, and then you take the magnitude squared. So we have these two probability amplitudes, and we know how they relate to actually measuring their outcomes. And we know that probability in general has to add up to 1, which just says that something has to happen, and your probabilities always have to accumulate to 100%. So from that, we can derive the following restriction on what these amplitudes can be. We have that the alpha up magnitude squared plus alpha down magnitude squared has to be equal to 1, because these are what the probabilities are, and you can only have in a qubit one of two states, which is this state and this state in this case. Okay, now I want to introduce some notation that's going to make our lives a lot easier. And this notation is called Dirac notation. It's named after the physicist Paul Dirac. And basically it goes like this. So if this is some variable, we'll give it the Greek letter psi. We want a way to denote that psi is referring to a complex vector of this form. And we do that by surrounding it with what we call a ket. And the ket just looks like this. It's the arrow in front and then this vertical bar. And we can also define something that's sort of like the complex conjugate of this ket, and we'll call it a bra. And this is analogous to taking the conjugate of any complex number, but doing it with a vector. And when you do it with a vector, it's not enough to just conjugate every element, but you also have to take the transpose of the vector. So if this ket is equal to alpha up and then alpha down, like this, then this bra is the transpose of that, and also conjugating all the elements. Okay, so now immediately I should note that what happens if you multiply a bra and a ket of the same vector? Well, then it's literally just a 1 by 2 times a 2 by 1 matrix multiplication. And if you're familiar with linear algebra, this just gives you a formula for the dot product, but we don't call it a dot product with complex vectors, we call it the inner product. And it's literally just multiplying this element by this element, and then this one by that one, and adding them. And this essentially gives you a measure of how aligned two different states are. Now, if they're the same state, this should be equal to 1. And it's neat that we already know this is equal to 1, because what is this? This is literally just the magnitude squared of this probability amplitude plus the magnitude squared of this other one. So already we have some connection with this kind of notation and our probability interpretation of quantum mechanics. And now we're going to start to shift over to the quantum computing formalism. Firstly, let me just say that this vector here, this complex vector, can be rewritten as alpha up times this vector plus alpha down times this other vector here. So what we have is that this vector here represents a purely spin up state, and this one represents a purely spin down state. So, and furthermore, it's clear that these two vectors are orthogonal. And if you take the inner product of 1, 0 and 0, 1, you're going to have 1 times 0 plus 0 times 1, which is 0. So two orthogonal vectors form a basis for the two-dimensional complex vector space that we're working with. And in quantum computing, in particular with these spin up and spin down basis vectors, we call it the computational basis. Because now we're going to abstract spin up to the state 0 and spin down to the state 1. Or you could do it flipped. It doesn't really make a difference. So now we have this 0 vector, which we can define as 1, 0, and this 1 ket vector, which is 0, 1. So any generic quantum bit, we'll call it Q, can be rewritten with two complex amplitudes. The first one corresponding to the 0 state, and the second corresponding to the 1 state. And this gives us a nice analog to classical computing, where we just take a series of bits and apply some operation to get out a new series of bits that could be whatever we wanted to compute. And now instead of these bits, we're working with these qubits. And the goal of quantum computation is to design a circuit, I'll call it a QPU, such that your output bits give you some information or compute something nice for you. And this video series is going to go over different algorithms in quantum computation. And in the next few videos, we're going to take a look at some very basic quantum gates that we can apply to our qubits, and also go over some of the restrictions that arise when you're working with quantum computation rather than classical computation. So one thing to note before I end this video is each qubit is a vector. So it's just this alpha beta vector. This is equivalent to what we have up here, because 0 is just 1, 0, and 1 is just 0, 1. And if we're working with vectors, it's fitting that instead of classical logic gates, which just take in some binary input and produce an output that could be either taking the or the and of two bits, or reversing the bit, negating it. And instead of those types of logic gates, what we have, since we're working with vectors, is linear transformations on those vectors, which is just represented by matrices. And in this case, it'll be a 2x2 matrix because we're working with two-dimensional vectors. And in the next video, I'm going to talk about a restriction on these vectors on these matrices, because it's not the case that we can just apply any willy-nilly linear transformation on a vector. They need to fit a certain requirement, and that requirement is called unitarity, or unitary. The matrix has to be unitary. And we'll talk about what that means both mathematically and physically in the next video. And then once we've laid that out, we can start going over some simple unitary matrices that we can apply to qubits and see how they transform, see how they evolve. And then we can start thinking of evolving our qubits in a way to compute something for us. And we'll go over the formalism for designing quantum algorithms. So, thank you.